All right, today we're going to talk about magnetic fields. Okay, so by the way, here's a picture of maglev train. We saw a little video of magnetic levitation using superconductors in the last chapter. The train is based on that concept. Okay, so here are some of the topics we'll talk about. We'll introduce magnetic fields and the forces that these magnetic fields exert on charged particles. You'll see that for a charged particle to feel a force due to magnetic field, it has to be moving. Okay, so we'll look at that. We'll look at the magnetic force on a current carrying conductor. We'll look at the torque on a current loop, and we'll look at the motion of a charged particle in a uniform magnetic field. Also, we'll briefly mention the Hall effect. All right, so here's what's coming up the next few chapters. Today we'll talk about magnetic fields and the force that they exert on charged particles. In the next chapter, we'll see that the magnetic fields are produced by moving charges. Okay, so let me go advance one slide. So here are the four Maxwell's equations that summarize all electromagnetic phenomena. So B represents magnetic fields. And what this equation is telling you is moving charges, this is current density, moving charges produce magnetic fields. That's what we'll study next chapter. Here's the second term. It turns out that time varying electric fields also produce magnetic fields. Okay. So you see epsilon naught times del E by del T. That is behaving just like a current, and this is called a displacement current. But anyway, time varying electric fields also produce magnetic fields. But next chapter we'll see that currents produce magnetic fields. That's what we'll study. Okay. But so that's that chapter. And then we'll talk about electromagnetic induction. What this chapter is about is this equation. What that chapter tells you is time varying magnetic fields produce electric fields. Okay. And that's the following chapter. So we'll be studying these four equations piecemeal in various chapters. And then we'll talk about inductance. Okay, so that's where we're headed. Okay, so here are the four Maxwell's equations that summarize all electromagnetic phenomena. All right, so let's talk about magnets. You guys have all played with magnets, so here are some various shaped magnets. It turns out that all magnets come with two poles, a north pole and a south pole. And like poles repel each other, and unlike poles attract each other. Okay, so every magnet, regardless of its shape, has two poles called the north and the south pole. Like poles repel each other, and unlike poles attract each other. And the force between two poles varies inversely as the square of the distance. So what that means is if you double the distance between these two, the force will decrease by a factor of 4. Okay, so that's what that means. All right, monopoles are, okay. So if you, for electric charges, you can go by just a positive charge or just a negative charge in a store. Now, you can't go to a store and just buy a north pole, okay? So they always seem to come in pairs, okay? So magnetism is different in that sense. So electric charges, you can just get positive or negative charges. But for magnets, it seems like you always get a dipole. Okay, There are some theories that postulate monopoles. These theories postulate the existence of just a North Pole or just a South Pole. And we haven't seen them yet, but there are some theories that postulate it. And that's what I wanted to mention. So now if you try to make your own monopole, you go buy a magnet, break it into two, and what ends up happening is you get two magnets. And you can keep going this till you almost reach the atomic level. So, okay. And of course, this never happens. So when you break a magnet, this is what happens. Okay, okay, so here's a magnet. And around this magnet, all the way to infinity, there's a magnetic field. And of course, the further out you are, the weaker the magnetic field. The way to sense this magnetic field will be you use another magnet. A little compass needle is another magnet. Okay, so this compass needle, there's the north pole of the needle, there's the south pole of the needle. The north pole of this magnet attracts that south pole, and the north pole repels this north pole. This south pole attracts that north pole, this south pole repels that. So the net effect of this magnet is, the net effect of this magnet on that magnet is it'll line it up like this. If you place the compass needle there, it lines up there like that. You see, so these needles line up along field lines. Okay. So that's what we're saying here. Magnetic fields exist around a magnetic material. So here's a magnetic material, and magnetic fields exist around this. So this was one of the things we mentioned. Moving charge particles and time-varying electric fields are sources of magnetic fields. So what this bullet point is saying is the following: moving charges and time-varying electric fields are sources of magnetic fields. So that's what we are saying here. Okay. Magnetic fields are denoted by B. Okay. So magnetic fields at a point can be defined in terms of the force they exert on a moving charge. Okay, we'll come to that in a second. So, but let me show you this simulation. So, for instance, if I bring this pole, the south pole is attracted to the north pole. Okay. And if I bring the compass over here, okay, so the north pole attracts the south pole, and the south pole attracts the north pole. Okay. So anyway, if you use this compass and went around, so you could trace these field lines. So here's the magnetic field around this bar magnet. And you can see that the magnetic field strength it's strong near the poles and then weaker elsewhere. Right, so it turns out that around the Earth, you can walk around using a compass needle. So there's the Earth, there's the North Pole of the Earth, there's the South Pole of the Earth, and it appears that, well, the magnetic field around the Earth is like that of a bar magnet. Okay, so here is the magnetic field of the Earth. Again, magnetic fields are denoted by B. Okay, so, and in a later chapter, you learn that this magnetic field is because of a current in the liquid core of the Earth. Okay, so the electric current in the liquid core is what produces this magnetic field. Okay. But again, we'll talk about all of that later. All right, so here's the field around a bar magnet. Now, if a region has a magnetic field, so let's say there's a magnetic field in every room on Earth, the Earth's magnetic field. The way to sense that magnetic field is You grab hold of a charged particle and throw the charged particle, and if it feels a force perpendicular to its motion, then there's a magnetic force, a magnetic field in the room. Okay, so and that's what we're going to talk about now. So the magnetic force. So B is the subscript B telling you it's a magnetic force on a charged particle. Q is the charge of the particle, V is the velocity of the particle, and B is the magnetic field. Okay, so if the particle had zero charge, there would be no magnetic force. If the velocity was zero, there would be no magnetic force. Okay, so for a particle to feel a magnetic force, it has to be charged and it has to be moving. Okay, and the magnetic force is V cross B. So it's a cross product. Okay, so if the charged particle were moving in this direction and the magnetic field were in that direction, the force would be in this direction. Okay. So the force is zero on the charged particle at rest. If V were zero, the force would be zero. And if the particle moves parallel to the field, then the force is zero. So if V was parallel to B, then the cross product is zero. And if V was anti-parallel to B, then the cross product is zero as well. Okay. So if you took a charged particle and threw it in the presence of a magnetic field, the only time you wouldn't feel any force is if you would throw it parallel to the magnetic field or anti-parallel to the magnetic field. Okay. Now, let's figure out the direction of this force. So there's the force, and there's the magnitude of the force. The magnitude of the force is QVB sine theta, where sine theta is the angle between the velocity vector and the magnetic field vector. There's theta. Yeah. All right, so here's how you figure out the direction of the field. Okay, so the force is a cross product, B cross B. Okay, and for a cross product, you take the first vector and there's the second vector. So, and the cross product will point in this direction. The cross product is perpendicular to the plane containing the two vectors. Okay. Now, here's how you remember this, or you can use your right hand. Your thumb is the direction of the velocity, and your forefinger is the direction of the magnetic field, and your middle finger points in the direction of the force. Okay, so here's one way to figure out the direction of the force. Okay, again, the important thing to remember is the force is perpendicular to the plane containing V and B. Okay, now here's let me try and show you on camera if I can figure out. Where is the? I don't know where the camera went. Oh, there you go. All right, so what you do is, I don't know if you can see my hands clearly, but here's a way to remember. Okay, you take the first vector, which is V, and the second vector is B. If you turn from the first to the second vector, if you turn a screw in that direction, the screw would move in that direction along your middle finger. And that is the direction of the force. Okay. So what you want to do is, here's another way of doing it. Take two pencils or whatever. So if this is the direction of the velocity vector and that's the direction of the magnetic field vector, if you turn from the velocity to the magnetic field, if you turn a screw in this direction, the screw would move toward me. And that is the direction of the force. Okay. So now you'll have to figure out the direction of the force. And you'll have to picture three-dimensionally for a lot of these problems. So make sure you understand that. Okay. All right. Okay, so this, again, the right-hand rule gives you the direction of the force. Again, so there is the velocity vector, there's the magnetic field vector, and the force is perpendicular to the plane containing these two vectors. Now here's the deal with the magnetic force. So if you have a charged particle that's moving, the magnetic force is perpendicular to the velocity of the charged particle. So what that means is, now let's say if you push a car, you can speed up the car. Okay. But since this force is perpendicular to the direction of motion, this force does no work on the particle, on the charged particle. So a magnetic force cannot speed up a charged particle. All it can do is change its direction. So that's what we're saying. Electric force on a charged particle is in the same direction as the field, whereas the magnetic force is perpendicular to the direction. Since the magnetic force are perpendicular to the direction of force, magnetic fields do no work on particles and hence do not change their kinetic energy. So a magnetic force cannot speed up a particle. Okay. All right, now let's look at the units for magnetic fields. Whenever you want to look at the units of some quantity, go to an equation that involves that quantity. So force was given by Q V cross B. Okay. So the magnitude of the force was Q V B sine theta, where theta was the angle between V and B. Okay. All right, so the units of B would be Q sine theta. Okay, so the units of B would be units for force are newtons. Okay. Units for charge are coulombs. Unit for velocity are meters per second, and sine theta is dimensionless. Okay. So there is the units for B, and which is units. And sometimes it's written like so. Coulombs per second is amperes. So ampere meter. Okay. And this combination of units is called a Tesla. Okay. All right, so the units for magnetic fields are Newton Coulomb per meters per second, and Coulomb per second is an ampere, so Newton ampere meter. And this combination is called a Tesla. Now, the Earth's magnetic field is, the Tesla is a large unit, is a very strong magnetic field. So for instance, I don't know if you guys have had MRIs, but MRI machines have magnetic fields of the order of 2 and 3 Teslas. And so let me show you an MRI machine. So just to show you how strong the magnetic field of an MRI machine is. Okay, so this is the picture. This is an all-time MRI. And as you can see, the patient is inserted inside the strong magnetic field. This is a metal gurney. And so what happened was somebody turned on the MRI machine while the metal gurney was in the room, and the gurney went flying into the MRI machine. So that's how strong the magnetic field is. Okay. So, all right, so Tesla is a very strong magnetic field. The strongest magnetic field we've made are about 100 Tesla, and these are in high magnetic field national labs and stuff like that. Anyway, so the Earth's magnetic field is about 1/10,000th of a Tesla. And so we define another unit called Gauss, And 10,000 Gauss is 1 Tesla, and the Earth's magnetic field is about half a Gauss. So you'll hear these two units, but the Tesla is the SI unit. Okay. And this, the unit is named after Mr. Nikolai Tesla. Okay. The Tesla car is also named after that. By the way, so here's a Nikolai Tesla joke. Apparently after Einstein had become famous and all that, a journalist was interviewing him and he asked Einstein, so how does it feel to be the smartest man on the planet? And Einstein apparently replied, I don't know, go ask Tesla that. All right, so here are some magnetic fields that we encounter. A strong superconducting magnet will produce a 30 Tesla field, 30 to 100, I guess. A lab magnet, a conventional magnet, not a superconducting magnet, can produce up to 2 Tesla. MRI units have fields up to 1.5 Tesla. The stronger the field, the more expensive the MRI. Okay. And the stronger the field, the better the resolution of the MRI image. Okay. And if we have time at the end, I'll tell you how the MRI machine works, but we'll see. When you go to a store and buy a bar magnet, it's 100th of a Tesla, which is the same magnetic field strength as on the surface of the sun. On the surface of the Earth, it's 10,000th of a Tesla. Okay, like I said, half a Gauss. This is a Gauss, and so half a Gauss. And inside your brains, every time your nerves fire, there's a current moving, and every time there's a current, the current produces a magnetic field. So you can study what part of your brain is active just by detecting the magnetic field outside your brains. Okay. All right, here's a map of the Earth's magnetic field. The Earth's magnetic field, as you can see, is not uniform. These are in Gauss. Okay, so it's strongest near the poles, okay, the magnetic poles, and weakest there. So, like we said, the Earth's magnetic field is produced. The Earth's magnetic field is as if it's that of a bar magnet, and this really is because of the an electric current in the liquid outer core. Okay. And apparently we are in the middle of a magnetic flip. So again, there's the North Pole, there's the South Pole, and this pole, this magnet is in the middle of a flip. So if you come back, let's say another 10,000 years from now, the magnetic pole will have flipped and all your compass needles will point in the opposite direction. Okay. But you'd have to come back in about another 5,000 years. Yeah. So this magnetic flip, so when this magnetic flip happens, what really is happening is the current direction in the liquid core changes. And we don't quite understand why it flips, but it flips on the average every 250,000 years. Okay. And the last flip happened 800,000 years ago. So now we're in the middle of a flip. All right, so anyway, that was just a side story. All right, so in a lot of problems, we will have to picture three-dimensional stuff. We'll have to draw vectors in 3 dimensions. And so here's a convention. When you want to indicate a magnetic field coming out of the plane of the paper or perpendicular to the paper, coming out of the plane of the paper, this is how we indicate it. And what you want to do is imagine an arrow, okay, and there's the head of the arrow, and there's the tail of the arrow. Okay, so when you're looking at the head of the arrow, so if you're looking from this direction, you're looking at the head of the arrow, and what you see is a point. And if you're looking at the tail of the arrow, so what you'll see is a cross. Okay. So if the magnetic field is coming out of the paper, then that's how we indicate the magnetic field. And the magnetic field into the paper is, you're looking at the tail of the arrow. Okay. So that's how that's indicated. All right, I will pause for a second, and I will give you